Sometimes students complain that mind maps are not effective and they're not helping them study. Okay, so some students will draw a mind map. For example, they're learning quadratic equations and they'll write down quadratics in the middle. Maybe this is the topic. Okay, they'll put a circle around it and they'll say, oh, quadratics, we have the quadratic formula. Okay, that's what it says in the textbook. So in quadratics, you use a quadratic formula. And then the quadratic formula is, say, x equals minus b plus or minus square root of b squared minus 4ac over 2a. And then in quadratics, you've also got x-intercepts. The textbook started talking about that. So then they'll put x-intercepts, and then they'll say that's when, okay, y equals 0, like this. Okay, so maybe that's something, okay, that's what their mind map looks like. But then they'll also complain that this mind map does not help them study at all, okay? They can't remember anything. They're not doing well in their maths tests, so they complain about it. Okay, so the problem with this mind map is that, yes, there's arrows on the page and it looks like they're making connections. But in reality, it's not that different from linear note-taking because the connections are often just taken from the textbook, okay? So this might be the textbook subheading, okay? And then the definition given by the textbook. Okay, there's not much thinking involved in this mind map, and that's why it's not useful. So in order to make a mind map useful, there's a few things that we need to think about. We need to make sure that we're really making connections. Okay, so properly making connections, and I'll talk about how to do this soon. As well as using our own words. Okay, and your own words can be like a simplified version of the definition or whatever makes sense to you, okay? You can use, and just in terms of connections as well, it doesn't just have to be connections about the topic. Analogies are also connections, and analogies are basically connections to other topics, okay? So other things. So for example, I might say studying is slow, and maybe it's as slow as something else, which is like grass growing is also slow. So this is some connection, but it's quite different, okay? So that's an analogy. A more useful way of studying quadratics, okay, is, okay, so let's apply this. So let's write in our own words what the textbook has given us, okay, by simplifying. So instead of just writing this quadratic equation as the textbook has given it to me, I can think about it a little bit more and put it in my own words, okay? So this quadratic equation starts with x equals, okay, what is this x? Well, when we're using the quadratic formula to solve for something, it's often solving for the x-intercept. So I can rewrite the quadratic formula as the x-intercept, okay? The x of the x-intercept equals, okay? And then we've got this mess here, okay? That's not simple enough for me. I'm going to simplify it. I'm going to think about how I can make it simple, okay? And maybe parts of the quadratic equation, if you look at it for long enough, you realize that they're actually quite familiar. So this negative b over 2a part might look similar to what you've seen in when you're solving for the x coordinate of the turning point. Okay, so let's just write turning point, TP for turning point. And then this part here looks similar to another equation, here our discriminant. So plus or minus discriminant, and this also has to be over 2a as well. Let's not make it incorrect. Okay, so I've already made some connections here. I've connected my quadratic formula to x-intercepts. I've connected my quadratic formula to the turning point, and I've also connected my quadratic formula to the discriminant. Okay, and just to further solidify it in my head, I'm going to think about why this makes sense. Okay, so when we're solving for the x-intercepts, okay, let's make a connection by drawing the visual graph as well. This is my parabola. X-intercepts would be here. My turning point would be, let's just pretend that it's center here. Okay, so my turning point, and then what does plus minus mean? Okay, turning point is here. If I add something to the turning point, I will get there. And if I subtract something from the turning point, I'll get here. Okay, and I also know, okay, let's make another connection, that my parabolas are always symmetrical. And so I'm always adding the same thing here, which is why this number, whatever this number is always the same. It's always square root of discriminant over 2a. Okay, so there's another connection. Okay, I can even go further and make even more connections. So discriminant, what else do I know about it? Okay, let's also connect to other things that we know about the discriminant. When the discriminant equals to 0, we have one solution. Okay, so when we're here, if we don't add anything to it, we have one solution. Okay, so why does that make sense? Let's draw another graph. If I don't add anything to my turning point, then I have one x-intercept. So I can see that I'm not adding anything. I don't add anything, then I end up here. That's one. So that makes sense now. I understand how we get to there. If the discriminant is greater than 0, if I'm adding things to it, oops. If I add things to it, then I end up with 2 x-intercepts. And from my diagram as well, I can see there are now 2 x-intercepts. So that makes sense. Okay, so that's why mind maps are useful. Okay, is when you make connections, but you can see that the way I make connections here is different to the, I guess, the generic mind map that students usually do. Okay, and another key point is to simplify things and to use your own words.